at certain intervals. So this could be every week, weekly deposits, or monthly deposits. For example, a monthly payment on a car or a mortgage. Or it could be like a payment deposited into an annuity, and this could be maybe once a year. So from there, of course, we're going to talk about sinking funds, and those are also another type of annuity. Now, from here, annuities, we have two kinds. One is an ordinary, and one is a due annuity. And so we're going to discuss the difference between those when we get to that section. But we're going to start just by using this sequence, and it is in fact a geometric sequence. You can think of all these numbers here being multiplied, and this one we can call it 5 to the power 0 times 1, because 5 to the power 0 is like we just have 1 times 1. So here this will be 5 to the power 1, 5 to the power 2, 5 to the power 3, and so on. So as you notice, we start with the first term, and then the second term will be 1 times 5. The next term will be 1 times 5 times 5. And the next term here, 5 to the power 3, is actually 1 times the previous two 5s, and then we multiply by another 5. And so each time what we're doing is we're just multiplying by another 5. And so that is what causes our sequence of numbers to be called a geometric sequence. So this geometric sequence is a finite geometric sequence, meaning that it has an ending term, a final term. And in this case, it will be the one where we're multiplying 5 by itself 6 times. So I'm just going to write that last one here. So it will be 5 times 5 times 5 times 5, and then another 5. Oh, and we also had a number 1 here. Okay, so to add this type of sequence, we do have a formula. And well, if we were to simplify it, it will just be written like we have it here on this example, right? So to simplify that and add them, we could use the fact that on the numerator we will have 5 to the power 7. So if our last term in this case was 5 to the power 6, we're going to increase that number by 1. So that's why the formula says 5 to the power 7. Then we're going to subtract a 1, and then the denominator will be the same 5, which we call it the base, right? We call base the number that is being raised to a certain exponent. So the base is still 5 minus 1. Now when we enter something like this on a calculator, we have to enclose the numerator and the denominator in parentheses. And sometimes we're going to have certain bracket around there, so that will be like another parentheses at the beginning and parentheses at the very end, but we will cover those examples. So whether you enter the sequence the long way or the short way with the formula, you could see here that you will obtain the same quantity. And so based on that formula, we could generalize that here. So imagine with our example, we had 5 to the power 6. That was representing n minus 1. So now n will be 1 more than 6, and that will be 7. And that's what we used on our formula here. So to refer back to what n will be in this case, it's going to be the number of terms, or the number of years. So in this case, we have an example, and this is an example of an ordinary annuity. And that is because the money that is deposited regularly is deposited at the end of each year. So that is our clue, at the end. That is how we know it's an ordinary annuity. And so we start with the first month. $1,500 are deposited. I'm sorry, the first year. The second year, another $1,500 are deposited. However, the account is going to earn 8% interest. So we could say that our rate is 0.08, and our time is going to be 6 years. Now, this graph right here is showing us how the deposits are being made at the end of each year. So here you start at t equals 0, but then here at t equals 1, after the first year has passed, the deposit is made at the end of the year. Then the next one is at the end of the second year, at the end of the third year, at the end of the fourth year, at the end of the fifth, and at the end of the sixth year. So in this case, we are going to have the first deposit was made at the end of the first year. Now at the end of the second year, another $1,500 go in, but we also need to account for the interest that the previous $1,500 made. So we're going to use 1.08, and this comes from that formula that we were using in section 5.2, the 1 plus R, or R over M. In this case, we're only going to use M equals 1 for the first problems. So if we can refer back to this as 1 plus I, and you know that I is equal to R divided by M, the rate in this case is 0.08 over 1 because it is annually. And so we could just refer to 1 plus 0.08. So if we add those two numbers, we will get 1.08 if you add these two numbers. And so that's what we're going to use for the interest that is being accumulated every year, 1.08. In this case, is multiplied to the power 1. Now for the third year, we're going to deposit another $1,500, and then this will earn 1.08, but now to the second power. So if we skip the ones in between, meaning the fourth and the fifth, so now I want to write the last one. What happens during the sixth year? At the end of the sixth year, another $1,500 will go in, and we're going to use the same number, 1.08, but now the exponent is going to be 6, just like the number of years that we have, to the 6th power. Now if you look at all this sequence, well, let's mention here this is the 6th year. So if we look at all these numbers, they all have one thing in common, and that is the payment, $1,500. So what I'm going to do is factor out 1,500, and inside the bracket, if I factor 1,500 from here, I will get 1. If I factor 1,500 from here, I will get 1.08 to the power 1. Now, if I factor 1,500 from here, I will get 1.08 to the power 2. And if I keep doing that, and I factor it from the last term here. If I factor the 1500 out, I will obtain 1.08 to the power 6. Now, this is a geometric sequence comparable to the one that we had at the beginning, with the first term being number 1, and then 5 to the power 1, 5 to the power 2. And the last term, I think for our example, it was also 5 to the power 6. I'm not sure about that. Yes, it was 5 to the power 6. So if we continue to do that, and in fact, I want to clarify something. If I had expanded my sequence, this one would have been the time is still considered to be 6, but for my last sequence that would have been to the power 5, because we started with the first year and we could imagine that being 1.08 multiplied to the power 0. So it makes sense that if the first year is to the power 0, the 6th year it will be 1 less, so to the power 5. Anyways, so right here we need to put a 5. Okay, so that would be the correction. Now, if we want to use the formula given to us previously, that geometric sequence formula, so it says x to the power n plus 1 minus 1, or in this case it says to the power m, divided by x minus 1. So in this case we have 1500, the numbers that we factor out, and inside here we're going to have 1.08 to the power not 5, because 5 is representing n minus 1, and we want this to be the power n according to our formula, and so for that n will equal to 6. And here the good thing is that you just have to look at what t equals, and that will give you the number that you need for your formula. So the problem previously, it did mention t equals 6, and so that's what we're going to use here. 6 minus 1, and here we will have 1.08 minus 1. Now for this formula, and I'm going to write it here, we're going to say the future value will be found by multiplying 1500 brackets, and we will have 1.08 to the power 6 minus 1. The minus 1 is not part of the exponent. And if we calculate this here, 1.08 minus 1, it is going to give us 0.08. So if we enter that on our calculator, it will have to be like this. 1500. This bracket will be our first parentheses. Then we need to enclose our numerator, so that will be 1 parenthesis here. Then we could enter 1.08 exponent 6. Then you must use your right arrow to get out of the exponent, or at least make sure that you're not typing anything in that little spot. So you move to the right side, enter minus the number 1. Then you close your parentheses to enclose the numerator, and then your division key, and then you could enter 0.08. And now we need to enclose the bracket, close the bracket, so that will be another parentheses there. So if you enter that correctly, you will obtain for the future